So here I'll talk about some supplementary mathematics about the Maxwell equation, which is called the differential form of Maxwell equations. Okay, so first I will introduce the differential form of the Maxwell equations, and then I will introduce another two theorem to actually show the equivalence between the integration form and the differential form. And then I will also tell you the final the Ampere-Maxwell's law actually match with the conservation of charge. Okay, so because when you learn chapter 29, you already have Ampere's law, and then in chapter 32 it tells you that we need to add something called a displacement current, so that it will be more correct. Okay. Maybe you will have a question whether we need to add the third term or even the fourth term to make it even more correct. The answer is no, because up till now it's already satisfied the conservation of charge, and that's why we also need the Maxwell's laws part for the Ampere-Maxwell's law. Okay, so here is the integration form that or the integral form that you have learned in different chapters, for the Gauss law in chapter 23, the Gauss law magnetism in chapter 32, Faraday's law in chapter 30, and Ampere's law in chapter 29. Okay, so I suppose you should have learned this in this semester. Okay, so so this is pretty much like that. Okay, so this is actually the same form as what we have learned. Okay, but here we would like to rewrite it a bit. We would like to we would like to rewrite it a bit. Okay, so for the Gauss law, we doesn't change it. We doesn't change it at the moment, but for the phi b, okay, so for the Faraday's, this one is the Faraday's law. Okay, so for this phi b, we try to rewrite it as a surface integral. This surface is enclosed by this Ampere loop. Okay， 就是这个 phi b 所算的面积是被这个 Ampere loop 所包围的这个面积。OK， 所以它们是两个积分是相关的。虽然它没有把它们的区域表示出来，但是这个面是被这个 loop 所包围的。OK，and similarly for the phi e, we also rewrite it as this surface integral. Okay, so this is the first change. Okay, this is the first change to the Faraday's law and Ampere's law. And then for the second step, we also try to rewrite another stuff. Okay, so for this one, the Q enclosed, we try to change it to a triple integral. So for the Q enclosed, this means the total charge enclosed by the Gaussian surface, 就是被那个高斯面所包围的总电荷。那我们把它写成一个 rho 是这个 volume charge density， 一个体积的电荷密度，然后对于体积去做积分，所以它积分回来就是这个电荷啊。那积分这个体积就是被这个Gaussian surface 所包围的。Okay, so this is the first change, and then for the second one, we also try to rewrite this I enclosed into this surface integral, and so actually we already learned it before in chapter 96. The current is the surface integral of the current density. Okay, current density, and then we try to integrate it over the surface. Okay, 所以这个其实我们之前也会的，而且我们 也改变了一下那个符号。改变什么符号的话，就是说，本来这本书里面它无论是什么维度的，它都是一个积分符号。但是有一些数学的课本的话，它会比较严格的话，就是说，比如说这个是面积分的话，其实是2维的嘛，一个面积嘛，一个面积肯定是2维的嘛，那它就会用2个积分符号。那这个是三维的，体积的话是3维的，所以用3个积分符号。这个也类似。This one is similar. And for the line integral, it is only in 1 dimension. Going through a line. Okay, so it's in 1 dimension, so that we still keep it as a single integral sign. And then for this one, a surface integral, 2 integral sign. And then also for this one, a surface integral, so that we have 1, 2, 3 integral sign for different types of integration. OK， 所以我们目前为止的话，对于我们之前学的这个书本里面的这种积分形式做了一些改变也不能说是改善，就是把它展开来，或者是把积分符号跟几维的就用几个积分符号。Okay, so we make some changes. Okay, so the next. Okay, so this is the differential form. Okay, so this is the differential form for all the four laws. Okay, so actually here. Okay, so here we try to compare. If we try to compare, so so on the left side is the integral form, and then on the right side is the differential form. Okay, so here we would like to use some analogy to show how to transfer it from integration form to differential form, although it's not so rigorous. And later on I'll show you a more rigorous way to show the equivalence. 那这里的话就先说它们怎么对应的它不是很严格的数学，只是让你方便记忆它是怎么来的。OK， 所以第一个的话就是，如果它是一个面积分的1，它就会变成这个倒三角1点，倒三角1点。那倒三角1点是什么东西？之前还没学过，但是你看过倒三角嘛？就是之前的话我们学过 v 倒三角等于应该是说负的倒三角 v 等于1，就是那个电场等于负的倒三角 v， 就是梯度嘛，这个是 gradient 嘛。那 gradient 1点的话，我们会叫做 divergence 我们叫做 divergence。OK， 所以这个面积分我们变成 divergence， 然后这个3重积分 ，so for this triple integral, it totally vanish. Okay, we only have this remain. And then of course this 1 over epsilon is another constant. So so this is how to transform the integration form to the differential form for the first one. And similarly, okay, we have this one. Okay, also for this is a surface integral. So we change this to divergence, and then look for the B field, and then on the right side is 0. So it's something like that. Okay, and then for the third one, okay, this is a line integral. We change it to the gradient with a cross. We will call it a curl. Okay, so this is this one. This one is called the divergence. Divergence. 中文叫做闪度闪度。这个的话我们叫做 curl， 叫做旋度叫做旋度，这个叫旋度，这个叫闪度。Okay. Okay, so we try to change this line integral of E to curl of E. And then on the right side, this surface integral just vanish. Okay, so we have only the minus d dt b. Okay, but b is a function of x, y, z, and t, so for different variables. So we change this d dt into the partial derivative like this. Okay, so similarly for the Ampere's law, okay, this is also a line integral. So for this line integral, we also change it to a curl of b, and then mu zero go to here, and then for this one, okay, like this double integral vanish, so remains a b. Okay, so also this double integral vanish, remain this j here, and then plus epsilon d dt. Okay, like this. So here epsilon partial t, and then the e goes to here, and also this surface integral vanish. So this is somehow an analogy between the integration form and the differential form， 就是它们怎么对应的，就是不是很严格的数学，就是告诉你说哦什么对应到什么，什么对应到什么，它没有一个很大的道理，但是你观察到就是这样啊，你如果不知道背后的数学是什么的话，大概是这个意思。Okay, so first I will introduce something called the divergence. Okay, so for the divergence, actually in chapter 24 I already introduced something called the gradient operator, 就是梯度嘛，梯度。Okay, 所以现在的话，梯度其实更重要的一个意义是 AI 的话 ，AI 的训练的话，其实是蛮常会用到这个 gradient 的，他们叫做 gradient descent， 梯度下降，就是去怎么去训练一个 AI 的模型，就是会用一个叫做梯度下降的一个 algorithm， 一个算法啊。因为怎么说，就是因为比如说一个 AI 的模型，它动辄可能几万、几百万，甚至几千亿的参数啊。如果像那种大模型，就是大语言模型的话，就是像 ChatGPT 那种的话，或者是国内的那种大语言模型的话，它们参数量是几千亿个参数，所以你要训练它的话，就是其实是你要对于一个某个叫做 cost function 的东西，你要把它弄到最小啊。那你们怎么求一个函数最小？比如说高中数学的话啊，求最小的话，如果不用微积分的话，可能用一些二次函数的话，可能你用一个配方法或者是什么。那如果你学过微积分的话，可能对它取导数。或者是甚至三角函数的时候，你可能把整个函数画出来，然后去看到最低的在那一点，那就是那个是最小的。OK， 但是我刚才说我们一个 AI 模型，它动辄那么多参数几千亿个参数，你怎么可能把整个模型求出来？怎么可能把它整个画出来呢？不可能嘛，几千亿个维度你连画都画不出来。所以的话，它就是用一个梯度的梯度下降啊，他们叫做 gradient descent， 梯度下降。那就是说我可能有一个起始点，我能算到的是这里的梯度。梯度的意思就是我往哪一个方向去走的话，它会变得最小。那我就往那个方向走一步。我走完一步之后，我再看下一个点的梯度，然后再继续往朝着最小的方向去走，一路走下去，它就有可能走到一个比较小的地方。用这个方式去让一个目标的函数最小啊，当然它不一定是全局的最小，它可能是一个局部的最小，但是至少它是一个可行的算法啊，所以 AI 的话，其实是非常常用到这个 gradient 的。OK， 所以这个 gradient 目前的意义是蛮有用的。Okay, so actually in chapter 24 we already learned this gradient operator in Cartesian coordinate. It is like partial x times I hat plus partial y j hat plus partial z k hat. Okay, and then here we have the divergence. Divergence is actually the gradient with this inner product. Okay, 所以它实际上的计算就是 gradient 跟后面的一个向量场 去做一个内积，去做一个 inner product， 就是这样。Okay, so for a vector field, we write it as f vector. Okay, it can be B field, E field, or any other vector field. Okay, so this can be applied for any vector field. Okay, but here I just use the letter F here to say that you can either apply it for B field or E field in the context here. Okay, so we write this F vector to be fx I hat plus fy j hat plus fc k hat. So fx, fy, fc 就是这个x, y, c 的 component. Okay, so here the gradient of f will be like this. Gradient of f will be partial x I hat plus partial y j hat plus partial c k hat, and then dotted with fx I hat plus fy j hat plus fz k hat. OK， 所以你们之前学过这个unit vector notation 去算这个 inner product 也好，或者是 cross product 也好。那 I hat 跟 I hat 去 dot， 它就会是1；I hat 跟 J hat 去 dot， 或者是 I hat 跟 K hat 去 dot 就会是0。就是自己跟自己去 dot 它会是1，自己跟别人去 dot 就会是0。所以只会剩下这个跟这个去 dot， 第一个跟第一个去 dot， 所以就会有这个 partial fx、partial x 出来。然后第二个 J hat 的话，只会跟 J hat 这一项有，其他都会是0。所以它就会有 partial fy、partial y， 还有最后这一个的话，它也只会跟第三个有so we have a partial fz, partial z, okay, something like this. So this is the divergence operator in Cartesian coordinate. Divergence operator. 所以值得注意的是，这个 divergence operator 作用到一个 vector field， 但是它出来的话是会变成一个 scalar field， 变成一个存量的场。这个是一个存量的一个 scalar field。scalar field。它在空间上面每一个点，甚至跟时间有关的，都会在每一个点、每一个时空都会有一个值。告诉你说一个物理意义，那什么物理意义 ？Okay, so here the gradient, the divergence of f, what it means? If the divergence of f at a point is larger than 0, which means this field f is like flowing out from that point. If divergence of f is smaller than 0, it is like the vector field f is flowing into that point. If divergence of f is 0 at that point, it is like there is no net flow in or no net flow out for that point. 其实跟我们之前学23章的时候是类似的，就是我们学这个 electric flux 的时候，如果那个 integration of E dot dA。integration of E dot dA 如果是大于0的话，它就是流出这个高斯面，流入的小于0的时候就流入，如果是等于0的时候就没有净流入流出，是一样的，只是现在的话是它不是对于一个高斯面来说，它只是每一个点它都会算这个东西，所以的话是它等于把这个高斯面缩得很小很小，无穷小，去看每一个点，它的是它是净流入还是流出，所以类似是这样，类似是这个意思。Okay, so let me finish the curl and then we have a break. So for the curl, we call it 旋度嘛，旋度。Okay, so the curl is like the gradient cross with another vector field. Okay, so you can also expect after crossing, it is still another vector field. Okay, 所以它们的最大的区别是内积的话，它会出来存量那 gradient 跟一个向量场内积完的话，它会变成一个纯量场。那这个 gradient 跟一个vector field 去 cross product 之后，它还是会维持着一个向量场，但是另外一个向量场。Okay, so here we would like to apply the curl operator to vector field f as before. So it will rely the curl and the gradient here, and then cross with this f. Okay, as I mentioned, so this ijk put in here, and then for this x component, the xyz component for the first vector, partial x, y, z will be put here, 1, 2, 3, okay, and then fx, fy, fz will be put in here. So if you still remember, we can do it like this. Okay, we have a I, okay, j, and then k, like this. Okay, so all these three are positive. So we have I hat, partial y, fc, okay, which is this one. I hat, partial y, fc, and then j hat, partial z, fx, j hat, partial z, fx, this one, and then k hat, partial x, fy, k hat, partial x, fy, this one, and then we have another three with negative sign. Okay, so this one with a negative sign, this one with a negative sign, and then this one all with negative sign. So the first one, I partial z, fy, I partial z, fy with a negative sign. So this one, and then j hat partial x, fc, j hat partial x, fc, and then with a negative sign goes to here. And then finally, k hat partial y, fx, k hat partial y, fx with a negative sign goes to here. Okay, so this is more or less the curl operator for the for a vector field in the Cartesian coordinate. Okay. 但如果这个步骤的话，是你不需要记忆太多的东西，你只需要把两个 vector 的 xyz component 写在这个行列式里面，然后去算左上到右下的是正，右上到左下的是负。那如果你想快一点的话，你也许记下来的话，这个是 x， 那所以这里有 yz 减去 zy，OK， 这个是 j 是 y 的话，那就会有 zx 减去 xz 然后还有的话是 k 的话就是 xy 减去 yx，类似是这样。Okay, so this is the curl operator. So for the curl operator, the physical meaning is like how the f field is rotating across every point in the space or even in time. Okay, so here, for example, we have an f field to be like this: yi hat minus xj hat. This is an assumed f field. Okay, we can actually plot it like this. For instance, okay, if we have let's say x equals 4, y equals 0, which is at this point. Okay, this is x equals 4, y equals 0. Okay, if x equals 4, this is negative 4, this is 0, so negative 4j. Okay, so you can see in negative y direction. And or for example, if I put in x equals y equals 0, okay, which is at the original point, okay, which is at the original point. Okay, so this is 0i minus 0j. Okay, so which is nothing here. Okay, or for example, if I put in xy to be 0, 4, okay, like this. If it is 0, 4, okay, so this is 0, this is 4, so this is 4i hat, 4i hat is actually this point. Okay, 4i hat is positive x direction, so which means that the f vector is pointing to the right side at this point. Okay， 所以你有兴趣的话，你可以尝试每一点都把 x y 的数值带进去它就可以画出来。当然正常的话，你可能会用 computer program 去把这个图画出来，比如说用一个 MATLAB 把这个向量图画出来。对，那所以的话就是说我们假设有这个场，那我们从视觉上看到这个图，它按照什么？它这每一点按照它的方向画这个箭头，而且会按照这个地方的那个向量的大小去画一个比较长或者是比较短或者是比较大的一个箭头或者小的箭头。所以从视觉上你已经看到这个向量场是顺时针在旋转的它就会表达成这个形式右眼看来已经是顺时钟旋转的。Okay, so if we try to take the curl operator to this f vector, okay, I don't try to repeat the whole procedure. You can just try to put this one into here, okay, or put this one into here, okay, then you will quickly get curl of f will be negative 2k hat. 什么意思？这个是 x 方向，这个是 y 方向，这个是 c 方向但是我们有画 c 方向什么意思？这个是它旋转的那个旋转轴，所以这个是negative 的 z 方向，负的 z 方向，因为这个是 x， 这个是 x， 这个是 y。那 c 方向的话，它一定会按照右手定则，就是 x cross out y。那 z 方向是 out of the page 的 ，z 方向是 out of the page， 而这个是负的 z 方向，所以它是这个 curl of f 是 into the page， 什么意思？如果我们用我的拇指指向里面的话，你的手指是顺时钟在转的，也就是跟着这个 f view， 这个 f view 在转的。所以它的意思就是我们实际上用这个 curl operator 的话，就会告诉你说这个 f view 它是以这个negative z direction 在旋转negative z direction 在旋转。所以这个是curl of f curl of f 会等于 negative 2k hat OK 是这个是指向里面的，是指向里面。Okay, so